Okay, so quickly about Imec. We are an R&D institute that also perform low volume manufacturing. Essentially, we cover all the TRL level that can be possibly made with this nanotech technologies. We are about more than 5,000. We have been growing considerably. We are now more than 5,000. Most of our revenues are actually out of industry. And we have two sites, one on 200 millimeter, one on 300 millimeter, and the 200 millimeter site is more dedicated for the most mature activities, including photonics and optics. But we are also expanding these activities in the 300 millimeter. So the infrastructure that we have on the 200 millimeter is based originally from a CMOS baseline 0.13. The 300 millimeter is more advanced, 65 to 28. We are, of course, well known to other people for the most advanced CMOS scaling, but I didn't put it on this slide. We are operated 24/7, and we have all kind of integrated photonics and flat optics type of technology together with the ability to manipulate different kind of substrates such as glass substrates. So when we look at our different platform, we essentially have pixels. So this is the active part. We're doing photonic, nano optics. We're also covering MEMS, 3D, and so on. And today, I will talk to you about meta-optic, multispectral, silicon photonics, silicon nitride photonics. We do have as well some activity on nano imprint lithography that is somehow related there, but I didn't have the time to cover that today. So when we look into what are we doing, essentially we are trying to manipulate light either by a form of a waveguide. So this is the yellow part. We try to couple in waveguide. There are some active functions, either detections or lasing that eventually occurs in such a way, or we can also manipulate the light in the Z direction. So this is essentially the difference between integrated photonic and nano optics. And there are for us critical aspects in terms of coatings and thin films. First is the feature size. Obviously, when you want to manipulate the light towards the lowest wavelengths, then things tend to be very small, specifically for meta-optics. The refractive index, in order to have a good core, the transparency is important. So at which point do you decide that you have a waveguide or not? It's actually a perpetual debate in the organization, believe me. But essentially, that's what it's coming down to, the transparency. And what we do care as well, which is somehow related, is the line edge roughness or eventually the surface roughness of the coating that we are using. So when we talk about integrated photonics, the most popular technology that we have is our integrated silicon photonics platform. It's based on crystalline SOI silicon. We do have as well LPCVD silicon nitride waveguide that can be integrated together with the platform. The platform is very complete, actually has been developed in our facilities, has been transferred to a production site where our PDK is running. And these are the people at the end that care the most about the control on thicknesses and on refractive index in the organization. There are other specific layers like germanium and so on that we are growing by epitaxy, which also need some careful processing. This is this first platform where you can see we are stacking the SOI, we are putting the silicon nitride, and then we have back-end of line type of processes that we are running. We also have a low-loss silicon nitride, and that one is the high-temperature nitride, which go into dB per meter range usually. So for some application, specifically in quantum, they are really chasing the photons. And we do use this platform for this kind of application where the losses are extremely important. For meta-optics, for those who are not familiar, the light propagates in the Z direction through the surfaces, and you are able to achieve different kind of function. So lenses is a very classical one, so flat lenses in that case, but you can also do color filtering, you can do beam shaping, you can also use it for doing some kind of a beam steering, shaping, display expander, and some people can also use it as a reflector. So the platform is very versatile. And it relies on this specific sub-wavelength resonances that actually occurs in the structure. We are using different kind of materials for that, starting from the low index, silicon oxide and quartz for the substrate. And then there is a lot of work going on doped glass when you're actually using the core of the glass also as a waveguide. So that is very popular in AR/VR. But we are also looking into the highest index material, niobium oxide, titanium oxide, and even amorphous silicon. They are, of course, not all transparent in all the wavelengths, but that is what you need to do, for instance, when you are operating in SWIR or above 900. We use the silicon because it has the highest index. Otherwise, we start to use a material like titanium oxide and niobium oxide. They are slightly different. There is perpetually a lot of debate in Imec and why we should use one and not the other one. And to cut a long story short, niobium oxide might be a bit lower in index, but actually is much more stable when it comes to temperature. And titanium oxide can still buy you some performance if it's processed in the right manner. We have been processing this different kind of structure. So with the silicon nitride on glass substrates. So these are structures that are either directly processed on the glass or that are actually layer transferred onto a glass. We do the work for niobium oxide and amorphous silicon. Here you can see some example of 200 millimeter wafer that have this flat optics type of structure. Another important item today, so we are post-processing imager wafer with Fabrication type of structure, so thin film interferometers. There, we are not going to rely on one or two layers, but clearly on a stack of very different layers where the uniformity, actually the optical path, is extremely important. This is something that we do in the organization. So each of these small blocks that you see there, you can see all the layer stack, is we coming and we are directly on the pixel processing a stack of thin films. The deposition is very important. We are working with Buller actually on the topic. I see they are later in the call. I think they'll be happy that they are cited here. But we do as well have, depending on the wafer size, other kind of equipment that we use. This is helping us to provide different kind of structure. So we have line scan, we have classical imaging with Bayer-like patterns. Depending on the wavelengths that you want to sort, we apply some different kind of processes. And the control on all the layer thicknesses is extremely important because the direct physical thickness is going to determine the wavelengths that you're going to filter. So here, a classical example of some filter material where we achieve about 90% of transparency at 400 something nanometer. You can see this is a typical layer stack that is being used. So the layers are not always uniform. We are sometimes doing some custom made thicknesses. We can etch quite straight. So the etching, I know we are not into an etching meeting, but actually once you have the good layer control, etching this material is also extremely important. And so far, this is what we can achieve. In general, etching very dissimilar material, classically in semiconductor manufacturing, it's a challenge. So we are also, welcoming input from the H2 vendors as well. As a conclusion, I've been running a bit fast, but I'll leave a bit of time for question. The first thing that comes to our mind for coatings is tight thickness and RI control. So when by tight thickness, I mean usually less than 1%. Well, this is really important. And actually, classical tools used in semiconductor manufacturing are a bit looser. They are also producing layers that sometimes are a bit more rough. So that's really a point where we are thinking for major improvement. When you go towards the edge of the wafer, usually this is where the machine vendors have not always been designing that so carefully. But rest assured that the etching guys have also been giving away the last centimeter of the wafer usually. At least on 200 millimeter for the older generation tool, on 300 things are a bit better. And which is also very important for us is the refractive index control. Some people don't always mention that, but having a very uniform control is nice for the thickness, but actually what matters is the refractive index, and there we are into 0.00x, even better than that. That is extremely important. So for instance, when you're forming thin films and there is slightly different microstructure, a bit more of crystalline phase or a bit more of an orientation, we will be quote unquote seeing that in the performance of the devices. And that is something we are watching very carefully. Now, the next generation of material, moving to the next point, we see today this industry has been, so for integrated photonics, they have been concentrated on crystalline silicon, polysilicon as well, amorphosilicon. Now they are going towards silicon nitride. These are materials that are quite interesting. Disadvantage of nitride is that contrary to silicon, you cannot produce active with it. So for the silicon nitride, we're also looking at adding new kind of material property. In the world of optics, there clearly we are relying on the refractive index contrast. So you need to be able to deposit very uniformly these thicknesses. You need to be able to pattern them. We are talking about pillars technology. So it is very common that you need to have several hundred nanometers of thickness of a layer and sub 100 nanometer pillars. And depositing the layer, being able to etch it is very important. And then you have the next step, which is to put oxide, the lowest index material. You need to be able to do gap fill. And that oxide, it's not very often cited, but sometimes induce as well optical losses because the people that work on these depositions adding a bit their ingredient, the precursors and so on that are typically used in CVD processes, they also induce losses. Niobium oxide, titanium oxide, very important for us for the upcoming platform. We have been demonstrated niobium oxide as well as a waveguide. So the losses are not yet at the level of what we can reach with silicon nitride, but are today maybe in the range of what you can do with crystalline silicon. We are also seeing region of the spectrum that becomes more and more interesting. So the aluminum oxide for the UV transparency is very important. And we see these three kind of material really coming up. So for all the people that are working on coatings and characterization of these coatings, this is definitely an area of interest for us. Now it's maybe it is a bit out of scope, I don't know, but just want to mention that. So as I mentioned, only silicon is active. So when you apply the bias to it, then it can do things that the other material usually cannot. So we are looking to new kind of electro-optic material like thin film lithium niobate, barium titanate. These are more crystals. We actually need to have a crystal to produce the electro-optic effect. These will also require very tight control. So the thin film lithium niobate, normally it's an ingot that you slice and you eventually bond into something else. The barium titanate is today an MBE process. So it's very expensive, but it produces tremendous performance. I think there's plenty of work to be done for this audience as well for this material. Thank you for listening to me.